Hi everyone. This is the second part of the video on 7.2 where we're going to do some examples. The examples that I have in mind are going to use some of the techniques that we laid out in the chapter. So let's start by looking at the case where we have an odd power of sine or cosine. And so the example I want to look at here is something like the integral of, say, sine to the fifth of x cosine squared of x dx. Now I know the technique I'm going to use is going to be to reserve a copy of sine because I have an odd power of sine. Odd power of sine means reserve a sine of x. And then we're going to convert the whole rest of the problem into cosine so that we have the substitution u is equal to the cosine of x, because du will be sine of x dx in that case, negative sine x dx. How do we do that? Well, we'll start by writing this as sine to the fourth of x cosine squared of x, and then the reserved copy of sine that we're going to use for our du over here. Now I can't use the u substitution yet because u is supposed to be cosine and I've got all these sines running around. So I'm going to convert sine to the fourth into cosines by writing this as, you got to be careful here, this is sine squared of x squared times the cosine squared of x times the sine of x dx. I can only apply the Pythagorean theorem to squares, not fourth powers. So I'm going to rewrite this as sine squared of x squared so that I can replace sine squared with 1 minus cosine squared. Well, now everything I've got left in the problem is a cosine. And the only sine I have left is the one I've reserved to be the du. So I can apply this substitution and convert the equation. And what you're going to get is the integral of 1 minus u squared squared times u squared times du, and then the negative I'll just put out front. Now, before I work on this, I actually have to multiply all of this polynomial out so that I get a giant polynomial I can integrate. So what does this turn into? Something like 1 minus 2u squared plus u to the fourth times u squared du, which is negative integral of u squared minus 2u to the fourth plus u to the sixth du, which is minus 1/3 u to the third plus 2/5 u to the fifth minus 1/7 u to the seventh plus c. And then substituting back, you'll get minus 1/3 cosine to the third of x plus 2/5 cosine to the fifth of x minus 1/7 cosine to the seventh of x plus c. So typical example of how it works when you have an odd power of either sine or cosine. Let's look at one where we have, say, an even power of secant. And in the case where we had an even power of secant, we were supposed to save a secant squared and then convert everything else into tangents. So let's look at the integral, say, of tangent to the third of x times the secant to the fourth of x dx. So I have an even power of secant. So what I'm supposed to do is reserve a secant squared of x and convert to tangents. So let's do that. This is the integral of tangent to the third of x, secant squared of x, secant squared of x dx. There's my reserved copy of secant squared. The substitution that I want to make here is u is equal to the tangent of x, so the du is secant squared of x dx. I'm already set up for this. The problem is that I have these secants in here that aren't tangents. But now that I've got an even power of secants left over, I can convert all these into tangents using the Pythagorean identity. Remember that secant squared of x is equal to tan squared x plus 1. Well, now I can use my substitution. I get u to the third, u squared plus 1 du, which is the integral of u to the fifth plus u to the third du, which is 1/6 u to the sixth plus 1/4 u to the fourth plus c. Substituting back, we get a sixth of tangent to the sixth plus a fourth of tangent to the fourth plus c. Very straightforward and very similar. As an example of a somewhat nastier problem, let's look at the integral of sine to the fourth of x. So now we have an even power of sine. So even powers of sine mean the only strategy we have is to try to reduce this using the half angle identity. So I'm going to write this as the integral of sine squared of x squared. This is going to get replaced with 1/2 minus 1/2 of the cosine of 2x squared dx. There's no other way to do this. When I see only even powers of sine and cosine, I have to use the half angle identities. There's no other technique. Foiling this out, you get, let's see, 1/2 times 1/2 is 1/4. And then I think you get 1/2 of the cosine of 2x. And then positive 1/4 cosine squared of 2x. Ew, you say. I know how to do that, and I know how to do that, so I'm good here, and I'm good here, but crap, I've got this squared cosine, so I've got to keep going. I have to apply another half angle formula so I get this into a form I can actually integrate. So I got to go one more step. The integral of 1/4 minus 1/2 of the cosine of 2x. Okay, so I've got a 1/4, and then this gets replaced with a 1/2 plus 1/2 of a cosine of 4x. Because whenever I do one of these half angle formulas, this is half of that. Well, now what I've got is a bunch of stuff I can integrate. It's ugly, but I can integrate it. So to finish up this problem, we'll lay it out in integrable terms. 1/4 minus 1/2 of the cosine of 2x plus 1/8 plus 1/8 of a cosine of 4x. I can integrate every single one of those terms using very straightforward rules. The first thing I'll note here is that a 1/4 plus an 1/8 is 3/8. The integral of the cosine of 2x is 1/2 of the sine of 2x. The integral of the cosine of 4x is 1/4 times the sine of 4x. Now these problems are actually sort of difficult to check when you're done because we used a bunch of identities to get to here. If we want to go backwards to try to recover what we originally started with, you should note here that we have to do a bunch of identities when we took a derivative to figure out that this is actually the derivative of what we ended up with. Okay, so students really don't like dealing with even powers of sines and cosines. I'll try to stay away from doing much of that. They're computationally expensive and they're annoying, and it's mostly just algebra. I do need you guys to know that when you look at an even power of a cosine or a sine, that the half angle formulas are the only way to proceed. So you do need to know it. Okay, practice more examples, and I'll see you next week.